Welcome to the Ontario High School video podcast series on acid-base fundamentals. This is part 4. We're going to look at how to calculate the pH of a weak acid solution. So, welcome. We know that strong acids ionize 100% in aqueous solution to H plus or hydronium ion H3O+. And so if we know the concentration of the acid, we can find the concentration of the hydronium ion or H plus very easily. For weak acids, they ionize less than 100%. For that reason, we have to find the H3O plus concentration, and we'll use an ice chart and our equilibrium principles in order to do that. So the problem we'll demonstrate is we'll determine the pH of a 0.1 mole per liter solution of acetic acid and its percent ionization. Remember that acetic acid is also known as ethanoic acid. We first write the reaction. Here we have acetic acid plus H2O. We're going to have H3O plus and the acetate ion as our products. So in this case, the acetic acid or the ethanoic acid is our Bronsted-Lowry acid. Water is our Bronsted-Lowry base. Our initial concentration is 0.1 mole per liter. Remember that water, being a pure liquid, is not, we don't worry about its concentration in this problem. H3O plus and the acetate ion we assume to be 0 to start. There's going to be a change minus X, and for H3O plus and the acetate ion plus X. And at equilibrium, the concentration of acetic acid will be 0.1 mole per liter minus X, and the concentration of the H3O plus and the acetate ion will be X. So we set up our Ka expression, the A representing an equilibrium for a weak acid. And so we have our concentrations of H3O plus times the concentration of acetate ion divided by the concentration of acetic acid. And we represent those by X times X on top divided by 0.1 minus X on the bottom. Our Ka expression then is equal to X times X over 0.1 minus X, and we'll simplify that to X squared divided by 0.1 minus X. Because the Ka value of 1.8 times 10 to the negative fifth is so very small in comparison with the initial concentration of the acetic acid, one of the things that we can do is to see if we can simplify this a little bit further. So the way that we can do that is we can divide our Ka value by the initial concentration of the acetic acid, so 1.8 times 10 to the negative fifth, divided by 0.1, and then multiply that times 100. And what we want to do is find the percentage. And so our percent here is 0.018%. And essentially, a percentage that small means that the change in that 0.1 mole per liter is going to be so infinitesimally small that we can just assume that 0.10 minus X is pretty much equal to 0.10 moles per liter. And you'll see this work out as we calculate the value of X. And again, we show here the simplification since 0.1 minus X is essentially 0.1. And we look at that in terms of the significant figures. When we subtract the value of X from 0.1, in terms of the significant figures, it's still going to round to 0.1. So our Ka value is going to be equal to X squared divided by 0.1. The square root of our Ka value times the 0.10 moles per liter will equal X. So the square root of 1.8 times 10 to the negative fifth times 0.10 will equal 0.0013 moles per liter of the hydronium ion. Now that we know the value of X, we can go in and fill out our ice chart. So our change is going to be minus 0.0013 moles per liter for the acetic acid and plus 0.0013 moles per liter for the H3O plus and the acetate ion, the CH3COO minus. So when we take 0.1 minus 0.0013, that essentially gives us 0.099 moles per liter, and for the H3O plus 0.0013 moles per liter and the acetate ion 0.0013 moles per liter at equilibrium. Well, we now know the concentration of the H3O plus ion in solution, so our pH is equal to the negative log of 0.0013 moles per liter H3O plus, which is equal to 2.89. So we have determined the pH of this weak acid solution. Now, if we had a 0.1 mole per liter strong acid solution, the pH of the negative log of 0.1 would be pH of 1. And you can see the difference in a weak acid that does not ionize 100%. A 0.1 mole per liter of acetic acid has a pH of 2.89. The last thing that we need to do here is find the percent ionization of the acid. Now that we have the concentration of the hydronium ion, we can then divide that by the initial concentration of the acetic or ethanoic acid, and we take that times 100, and that will give us the percent ionization. So 0.0013 moles per liter hydronium ion divided by 0.10 moles per liter of acetic acid times 100 gives us a percent ionization of 1.3%. And here again you see the difference between a weak acid and a strong acid. A strong acid in aqueous solution will ionize 100%, a weak acid usually much less, and in this case 1.3%. Well, time to see what you have learned. Try this problem. I want you to determine the pH and percent ionization in aqueous solution of a 0.025 mole per liter hydrocyanic acid solution, HCN, and the Ka value for this is 6.2 times 10 to the negative 10th. I'd like you to pause the podcast and try and solve this problem. Use the same steps that we did before, and then when you're ready and have an answer, go ahead and resume the podcast and we'll work through it together. Thanks. Welcome back. Let's see how you did. Set up the ice chart. Know that a weak acid is going to donate, in this case, hydrogen ion to water to form H3O plus, and the cyanide ion, Cn minus. So here we have the ice chart set up, and we set up our Ka expression. So we have our concentration of H3O plus times the concentration of Cn minus divided by our initial concentration of HCN. So x times x divided by 0.025 minus x. We simplify our Ka expression to Ka is equal to x squared over 0.025 minus x, and then we're going to look at whether we can drop the minus x out of the bottom part of the expression, 0.025 minus x. So we take our Ka value, 6.2 times 10 to the negative 10th, divided by 0.025, and multiply that times 100, and we get 2.5 times 10 to the negative 6%. It's so very small. 0.025 minus x essentially is equal to 0.025. And there are different ways of looking at this. Some instructors will use what's called a 1% rule, meaning that when you do this division of the Ka by the initial concentration, if it's less than 1%, you can drop the x out of the expression. Others use a 5% rule. You have to make your own best judgment on that. I tend to use the less than 1%, means that you can drop the x, and so we're definitely going to drop it here. So since we have dropped out the minus x from the bottom part of the expression, our Ka value is equal to x squared over 0.025. To solve for x, which is the concentration of our hydronium ion, we take the square root of our Ka value times 0.025 moles per liter. It's equal to x. So the square root of 6.2 times 10 to the negative 10th times 0.025, we square root that value, and we get a concentration of hydronium ion of 3.9 times 10 to the negative 6 moles per liter. Since we have the hydronium ion concentration, we can now calculate the pH. So its pH is equal to the negative log of 3.9 times 10 to the negative 6 moles per liter hydronium ion, which gives us a pH of 5.40. Lastly, we just need to find the percent ionization. So we're going to take the concentration of the hydronium ion, 3.9 times 10 to the negative 6 moles per liter, divide it by the 0.025 moles per liter, multiply that value times 100, and we get a percent ionization of 0.016%. Well, we are at the end of part 4 of the video podcast series on acid-base fundamentals, and want to leave you with a quote from Mad Magazine's spokesman Alfred E. Neuman, since this is election time. How come we choose from just 2 people for president and 50 for Miss America? I wish you well. Stay tuned for part 5.